So share.
So I'll start recording too.
Okay, so I want to, oh, my screen sharing is disabled.
No, I did have one. Why?
That's okay.
1 second.
Take your time.
So maybe I able someone else. I able Hildebert. Yes.
Okay, great. iPhone, iPad. Today I'm share. Okay, screen mirroring. Okay, can you see what I have?
Yes, I can see.
Okay, great. So I just opened what I discussed last time. So I was talking about the Aubrey-Mather theory and actually the area preserving maps of the simplest imaginable kind, which actually contain all the information that people understand anyway, more or less. I don't, what I was thinking of doing today was, I think this discussion of the Mosers twist theorem, it maybe is a little bit too technical. And if, although there is a very short proof, obviously statement as well, of the theorem, and I think maybe it's best if I just give a reference to anyone who would like to know, to a short article which explains how to reduce the question of existence of invariant circles. So we have a twist map that preserves area, and unperturbed map simply rotates circles, geometrical circles, by the angle which smoothly depending on the radius. So it's a twist map. And if you perturb this map by sufficiently small perturbation, the KAM theorem, Mosers twist theorem, says that many invariant circles survive. That was a huge progress, probably the biggest result in the 20th century in this area in dynamical systems. But I will just give a reference to this, and I will maybe describe something that's fun and kind of entertaining, and at the same time an interesting thing. So this is the lecture 4 that was promised in the outline. I apologize that I kind of crumpled up the KM theory, but having to make a choice, I would put myself in the place of a listener, and I would probably like to hear this. So here is the thing that kind of amazed me when I was still in graduate school. I learned from, I don't remember who told me this, but anyway, this is an amazing phenomenon, an inverted pendulum that becomes stable, the upside down pendulum. If you vibrate the pivot point of the pendulum, then the pendulum becomes stable if you do vibrations with a sufficiently high frequency. If I can try to share the screen, I will maybe show a video.
Yeah, you can.
I don't guarantee that it'll work, but I'll try.
If there is an audio, you have also to habilitate the audio at the moment of sharing.
Yes, so I will open. I think that I can share the screen. Let me think. I'm sorry, I'm so bad in multitasking. So I will say share screen and the desktop. I think I should share the desktop. Yes. And I will do this. And I'll do this. Can you see this?
Yes, yes.
Okay, so this is a jigsaw that you'll see the blade vibrate in a second. Can you see the video?
Yes, yes, we can.
Okay, great. you see the vibration seems to act, it makes the rod want to align with the direction of vibration. Upside down pendulum is stable. Okay, so that's the stop share. Okay, and now I will share the screen again, but now with the iPad. I wish I was a little faster in this business, but.
No, no more.
Okay, all right, so here's a puzzling phenomenon. Here's the rod, let's say mass is concentrated at the end point, and the pivot point is vibrating periodically. There is no feedback. It's just dumb vibration. Why is the pendulum upside down stable? So I can write down the equation of motion. So I can write the equation for theta, for this angle theta. So you don't have to read it, but it's basically length times the second derivative of this theta plus negative g plus amplitude, let's say sine of omega t times theta equals 0. So this is a linearized equation. If I wanted to write the actual nonlinear equation, will be this. So that's the, and when omega is large enough, for some reason, theta will stay bounded. So one can prove this by averaging theory. One can make changes of variables and calculate, for example, in the book of Arnold on differential equations, he takes replaces the sign by the function plus minus 1 with the right rapid frequency, and then you can explicitly calculate what happens to theta after one period of oscillation, and you conclude that the motion is stable, but it still doesn't explain why it happens. And that kind of always bothered me. I knew this thing since graduate school, and one time a graduate student came into my office and he asked me this question: why is the inverted pendulum stable when you vibrate the pivot? And at that moment, it struck me that there is a simple geometrical explanation, which I would like to give. And maybe I should first say how, very briefly, how this problem is treated mathematically before I give this geometrical explanation. So the standard treatment, but I will skip all the technical details and just give the skeleton of the standard treatment, standard approach to proving stability. So you write this system as this equation as a system. So theta dot is omega. Omega is a good, probably I should say, this omega is not the same as that omega. Let me call it V. And V dot is minus, let's say, this is some function Q of t, sine theta, or more schematically, if we introduce the vector theta v, so this is the angle and angular velocity. It's a point in the phase plane, right? So we call this x, that's a two-dimensional vector. Then in the end, this equation is just of the form x dot equals to some matrix which depends on time times x. And I don't want to know much about this matrix. Basically, in this case, what is the matrix? 0, 1, minus q, 0. Oh, excuse me. I forgot. I want to linearize this. So I will replace sine theta by theta. So I will Okay, so this is the this equation just rewritten in a more geometrical way. Okay, so how do we determine stability? Well, we just look at the stroboscopic map or the Poincare map or the time advance map, it's called. We ask what happens to the initial condition. In other words, initial angle, initial velocity, angular velocity. What happens to it after one period? T is the period. In this case, it's 2 pi over omega. Doesn't matter. Okay, so Poincare map, that's given by some matrix called the Floquet matrix. So you can call this Floquet matrix as a stroboscopic map. It simply tells us what happens to any conceivable initial condition after one period. And that F contains all the information about stability. About stability of the pendulum. Why? Because if I want to know what is the angle and what's the angular velocity after many periods, I can, after n periods of oscillation, this is going to be what? It will be the initial information times this matrix to the power n. And so the vector x, in particular, its theta coordinate, which is the angle of the pendulum, is bounded. This vector is bounded by some constant for all n after any number of periods, if and only if this matrix F to the power n is bounded. Okay, so what does that mean? You take a matrix F and you take any power of it. By the way, what do we know about F? We know about F that its determinant is 1. That I should have said that. Determinant of the matrix F equals 1. Why? Well, this is a frictionless system. It's a Hamiltonian system, you could say. Oh, I'm sorry, this is times theta. Oh yeah, I have it. Theta is here. Theta was just written too far. Okay. So this is a Hamiltonian because this system, let's call it 1, is Hamiltonian, which is equivalently in 2 dimensions, its divergence is 0 of this vector field. That is divergence of this vector field. And what's this vector field? It is v comma minus q times theta, times theta. And let's calculate the divergence. So the divergence is the derivative by the first variable of the first coordinate plus the derivative by the second variable, which is v of the second coordinate. You see, v doesn't depend on theta, and theta doesn't depend on v, so the result is 0. So divergence is 0, and therefore the flow in the phase plane is preserving the area, which implies that the determinant of the mapping from time 0 to time t, that mapping preserves area in the plane. So that means the determinant is 1. So to summarize, I want to know the stability of the pendulum. That question is encoded in the property of the matrix F. And stability is equivalent. So the physical concept of stability is equivalent to the linear algebraic concept of the boundedness of the matrix F, whatever that means. You know, the matrix F is bounded for all n, okay? So quick question. So this is a linear algebra question. So keeping in mind that the determinant is 1 and the matrix is 2 by 2, what does it mean geometrically in terms of matrices? A determinant 1 matrix whose powers are bounded. Doesn't matter to what power you take the matrix, you get a bounded matrix. What does it say about the matrix? Well, it's equivalent to saying that the trace of F is no greater than 2. It's not exactly right because identity matrix has trace 2 and it's bounded, doesn't matter to what power. So maybe I should say more precisely, it's the other way around. It's almost true what I said, but basically if the trace is less than 2, then the matrix is constant. If the trace equals to 2, then that's a parenthetic remark. If the trace of a matrix and the determinant is 1, then F must be either 1, 1, 0 something, or F is 1, 1, 0 something. That's kind of an exceptional case. Let's not waste the time on it. What does it mean geometrically? This is algebraic statement. The trace is less than 2. What does it mean geometrically? All it means is this, that a matrix whose powers are all bounded is an elliptic rotation. In other words, it's similar to the regular rotation. In other words, it keeps ellipses invariant. That means any vector with a tip on the ellipse, if you take the vector x, fx will be on the same ellipse. That's this is equivalent to the statement that the matrix is constant. You see, okay. So this was kind of a quick background on differential equations and linear algebra. Stability of the inverted pendulum is equivalent to boundedness of the matrix, which is called the Floquet matrix also. Better name would be stroboscopic matrix, but stroboscopes probably didn't exist when Floquet lived, so it's called Floquet matrix. Okay, so the standard approach is, for example, how Arnold would do it. He would compute this Floquet matrix, which is a simple exercise. If you have sign replaced by plus minus 1, then you have an explicitly solvable equation, and you replace sine theta by theta, looking at small angle deviations. That's not unreasonable. And so he calculated this matrix explicitly and showed, then you write down the trace and you see that it's less than 2. It doesn't explain anything, but it makes sure it proves it, but doesn't explain it. Okay, so now I would like to give a geometrical explanation. So this thing, if you know all the background, then it takes about a page of calculation, plus the background you need to learn. But here's a proof that one can, well, an explanation of stability, which requires no background in differential equations, is just basically elementary mechanics. So let's look at, this is how the pivot vibrates between these 2 points. And let's look at the mass. Here it is. And so frequency of vibration is huge. So it's going really fast, like in that video. And the amplitude is small. Okay, so this is parenthetic. Okay, so here is kind of a naive argument. So all the mass, let's say, is concentrated here at the tip of the pendulum, okay? And because this frequency is very large, the acceleration is enormous. So this force, let's say this, at this moment, let's say this pivot accelerates up. This compresses the rod. What happened? And it acts with a tremendous force on this. And so I can say, loosely speaking, that this mass moves in the direction of the force. Of course, it's not strictly true. That's what Aristotle would say, that the motion is in the direction of the force. But let's make this as Aristotelian approximation. So let's say that, so approximately, it's actually true because of these two assumptions. Approximately true. Mass moves in the direction of the rod, let's say AB. What does that mean? If that is so, then the mass moves actually in a curve. You see, if you look, imagine you have a bicycle. This is kind of a top view of a bicycle, right? So this is the steering wheel. This is the body. And this is the rear wheel. So the steering wheel is A and the rear wheel is B. If you drive the front wheel back and forth, the rear wheel will travel in a curved path. So this is the tractrix, right? So this is the tractrix. Also the pursuit curve. And to summarize, you see, I'm not, so I'm kind of imposing an artificial constraint on this mass. I'm saying that it moves in the direction that is being pushed. I'm not interfering. So let me impose this constraint that it moves only in that direction. It's a very innocent constraint, right? I'm not interfering with this enormous force that acts like this, right? I'm just channeling it not to move left, right, so to speak, not to turn. But if you have a mass that goes back and forth along a curved path, what's going to happen? It will exert a centrifugal force, right? It will push against you are imposing curved motion on it, so it will resist with the centrifugal force, which is what? This force is proportional to the curvature of the curve times the velocity squared. That's basically the high school formula, which in high school we did this v squared over r, right? The centrifugal force. Well, 1 over r is the curvature. So it's the curvature of the tractrix. Now this is all I need to replace 2 pages of calculation in books like Landau and Lifshitz. Here's the forces. This force is kv squared. I guess I got to the main reason why the pendulum wants to be stable. There is the gravity, of course, which destabilizes, but this force we just discovered, you see what it does. It tries to straighten the thing. So I admit it's not a rigorous argument, but the condition for stability is if this force is greater than what? Than the destabilizing effect of mg, and that is what? Mg sine theta, right? If this is angle theta, then this is mg sine theta, right? And I should say forces mkv squared, mkv squared. Okay, so what is K? M cancels. What is K? Curvature of the pursuit curve, that's a very short calculation. It turns out to be proportional to the angle divided by the length of the rod plus high order terms. We're looking at small angles. Okay, and sine theta is approximately theta, so this equation becomes masses cancel, so theta over L. I keep only the main part of F, right? I just keep this, so I put theta over L, V squared. Now, V is the velocity in this direction, right? That's V. But if the angle is small, then it's approximately the same as the velocity u up to higher order terms, which we explicitly know. If we know the construction of our jigsaw, we know u. So I replace, so this was the curvature. This was curvature. V, I write u squared. And that has to be greater than mass, which was canceled, g theta. I replace sine with theta cancels, and we're finished. So the criterion for stability is u squared is, okay, I'll just leave it the way it was. Stability criterion is u squared over g over L is greater than g. You see, this calculation didn't take much time. But if you follow, and this calculation doesn't, of course, it's not rigorous, that's its minus, but its plus is it has a geometrical content and it's short, and it's, for example, the same calculation, even for the piecewise constant acceleration, takes, like I said, about a page in Arnold's book, or maybe two. But this calculation doesn't even care what kind of acceleration you have. You just need the periodic one thing I should say, this should be the average, right? Because I took this picture at a snapshot in time, but I really need to do the average because, you know, and I use smallness of the amplitude because I replaced, I say the curvature pretty much doesn't change much over the different points of this tractrix. Anyway, so this is a non-rigorous argument, but it shows that behind all this complicated algebra, there is a simple geometry hiding. So that's one item I wanted to say, and there's, one can analyze what happens if you have a more complicated system, for example, a pendulum with two legs, you know, like a mass, or with more. When you vibrate it rapidly, it's known that it is also stable with the rapid enough vibrations. In this case, a similar geometrical picture sits behind the complicated averaging procedure. So that's one thing I wanted to say. So that was just a little snapshot of this. Okay, if there are any questions, I'll be happy to answer. Then I'll go to the next topic. So if not, I will describe, there is another topological explanation of stability, but it's basically relying on a beautiful picture that is due to Gelfand and Lidsky, which I maybe describe because it's really nice to know. It's such a nice and such a basic thing that is just a gem that's worth knowing. So Gelfand, Lidsky. a picture of SL2R. Which is simply the set of all matrices, 2 by 2 matrices with determinant 1. And why do we want to consider these matrices? Because the Floquet matrix is determinant 1. So we want to understand when is the Floquet matrix an elliptic rotation? When is the Floquet matrix of an inverted pendulum is an elliptic rotation, i.e. when is the pendulum stable? Okay, but right now I just want to look at this very, very well focused question. So a determinant of f equals to 1. And here's the theorem, the set, I don't have to, so SL2R, special linear group. Special means determinant is 1, linear group of 2 by 2 matrices with real entries is topologically a solid open torus. The picture is this. So there is a one-to-one correspondence between the points. So this is, in other words, it's a circle cross an open disk. Two-dimensional disk. So to every point in the disk, one can assign a determinant 1 2 by 2 matrix in a continuous way. And let me just draw a picture. Actually, here is the identity matrix, for example, is represented by 1 point in this torus. Minus identity matrix is by another point. Let me redraw it. So it's really beautiful. It's a view of, you can visualize all the matrices at a glance, right? It's so identity matrix is represented by 1 point, minus identity by another point. Where do the matrices, so the matrices which are similar to rotation, so cosine, sine, minus sine cosine. These matrices form a circle, right? As you change theta, this is in one-to-one correspondence to the point cosine sine, right? So if you give a point on a circle, that's this guy, and that determines uniquely in one-to-one a matrix. So one of these matrices is identity. When theta is pi, it's a minus identity. So you see when theta changes, this matrix traces out a circle in the torus, right? What are the matrices that are similar to theta pi over 2 corresponds to this. This is minus pi over 2. This is pi over 2. The matrices that are similar to the 90-degree rotation. So when theta is pi over 2, we get a 90-degree rotation. Matrices similar to it, which you can get by multiplying by a matrix and its inverse on the left and right, that turns out to be a disk. And the same for the matrices that are similar to the minus pi over 2 rotation. Where are all the elliptic matrices? The matrices whose trace is less than 2. These are stable matrices. This is the name one uses, stable matrices, which, in other words, which have the trace. You know what I'm going to say? Yeah, trace less than 2. Okay, well, the trace could be between 0 and 2 positive. These are here. So I'm shading this. And the matrices with trace less than 2 but negative are here. So it's really a beautiful picture. It just shows how all the matrices sit together. Matrix on the boundary. On the boundary, for example, here, right? This matrix here is similar, is of the form 1, 1, 0, A with positive A. It's a matrix which is a shear, but in some direction, which is, depends on this matrix. Okay, so let me just prove this statement, prove Gelfand-Litsky's theorem that the matrices of determinant 1 form a torus. Okay, let's take any such matrix.
Excuse me, what's D?
D is it's a two-dimensional.
No, T, table, T.
Oh, T, for any T. So T is just a similarity.
Okay.
And one can choose T to have determinant 1 without loss of generality because that, scales out. For any T determinant 1. Yeah. Okay, so here is the proof that the matrices form a torus. So we can write this F as, this is kind of done with some x plus y, z, plus w, z minus w, x minus y. Okay, so I mean, there are 4 entries in the matrix. So instead of writing x, y, z, w, I write them like this, right? That's certainly, we can do that. Determinant f is, you see what happens now is determinant of f is, this is why I did this. It's x squared minus y squared minus z squared plus w squared, right? And that's equal to 1. I apologize. You know what? Let me do it in a, I mean, one can do it, but like this, but let me redo it. So let's write f instead, write a polar decomposition of f. In other words, write f as a positive definite matrix, symmetric and positive definite, times the rotation matrix. There is a unique way to write this. So there is a unique P and R, unique such P and R. Why is that so? Because we can actually calculate them. So we can look at the F transposed. I don't yet know. I'm proving that the polar decomposition exists. Assume for a moment that it doesn't. Let's see what P and R must be. So transposed is going to be R transposed P. Transposed by P is symmetric, so it's the same. And then we can take F times F transposed. Well, that's PR. PR times R transposed P, but R is a rotation matrix and transposed is its inverse, so it's just the identity. So it's P squared. So therefore, okay, so let's choose. So far, I started with something that I don't actually, that I don't know, it's true. But now now choose P to be the positive square root of FF transposed. Well, this is a positive definite matrix. It's also symmetric, of course, because if we take transposed, we get the same thing. We switch, right? So it's a positive definite symmetric matrix. Square root of such matrix can be defined how? So it's a positive definite matrix, and the square root is simply, you diagonalize it and take square root of the diagonal part, and that's what we mean by the square root. So more precisely, write F transposed as, by diagonalizing, write T times diagonal matrix times T, right? And diagonal matrix is with positive guys. These are positive. Why are these positive? Because FFT is a positive definite matrix. Because, right, is positive because if we take FF transposed, apply to any vector X and take the dot product of with X, we get F transposed X dotted with F transposed X, right? And F is non-singular, so this is strictly positive if X is non-zero vector. If X is a non-zero vector. So therefore, eigenvalues have to be positive. And so then we define square root of FF transposed, sorry, as simply T inverse square root of the diagonal matrix, which is simply what matrix with square roots on the diagonal T, then T inverse diagonal T square. I want to show that this is a genuine square root, so I have to square this, which I'm doing, and I want to show that we get FF transpose. So let's see, we get T inverse square root of diagonal times T multiplied by the same thing. And so T and T inverse produce identity, and D times D square root just produces D, because square root of D is just the matrix with roots of lambda on the diagonal. So it's T inverse DT. And that is indeed FF transposed. Okay, so indeed this this qualifies as a genuine square root. In summary, so I produced P, and then you can write R here, write R as F times P inverse on the left, P inverse times F. And it's a simple matter, which is not very instructive, to show that R is indeed a rotation matrix. In other words, that R satisfies R transpose R's identity. Okay, so coming back to the starting point, we took any matrix F, we wrote it as a positive definite times the rotation. Geometrically, what does it mean? That any matrix can be, you see, what's the geometrical meaning of this polar decomposition? It says that every matrix, if you rotate let's see, so if you apply a matrix and then you rotate appropriately, then what you get is a hyperbolic rotation. Okay, anyway, so now, so this is determinant 1 by definition. That's what we start with. This is a rotation matrix, therefore its determinant is 1. Hence, P has determinant 1. The positive definite matrix has determinant 1. So, but P is a symmetric matrix, which means I can write it as X, Y. It's symmetric, so Y is here too. And here I write X plus Z, and I write X minus Z. So positive definite. And determinant of P is 1. Therefore, X squared minus Z squared minus Y squared equals to 1. Which means that X is square root, well, X squared, let's say, square root of 1 plus Y squared plus Z squared. So that's 1, sorry, X, not X squared. And furthermore, now the question is X positive? Could X, I didn't write plus or minus, right? I solved this for X, but I only wrote with a plus. What right did I have to do that? I had the right to do that because I said P is positive definite. That I have not used yet. I only used the determinant equal 1, but I did not use P positive. So P is positive definite matrix implies that the trace of P is positive. But the trace of P is what? It's 2x. So that's why I did not put a minus. Okay, so to summarize, the matrix P, for the matrix P, it's of this form. And if you know Z and Y, X is uniquely computed, right? Y and Z determine everything, determine X and therefore the whole matrix, right? P is parametrized by Y and Z, which is a point in R2. So in other words, we have a one-to-one correspondence between the plane, the points in the plane, and matrices P, positive definite matrices of determinant 1. That's kind of a nice fact to know in principle, right? The set of all positive definite matrices of determinant 1 is topologically just R2. And R2 is the same as an open unit disk, okay? So P is topologically the same, the set of matrices P is the same as the open unit disk. Okay, now, and the rotation matrices are the set of all rotation matrices, as I already mentioned, is topologically a circle, because these are of the form cosine, sine, minus sine, cosine. And so, therefore, we conclude that the set of matrices PR, which is the set of all matrices F in SL2R, this set of matrices is topologically just the product of the circle with the unit disk in the plane, and that proves the theorem.
Is there a similar result when the determinant is -1?
Oh, it's a good question. I never thought of this. It's got to be, because these maps can be realized as a composition of the ones we just discussed and the reflection. So yes, I think so.
Okay, thanks.
Yeah, thank you. That's a good question. I never thought of this question. Okay, so this is a beautiful thing. Now, how do the stable matrices, how do we explain the picture that I drew? I claim that the elliptic matrices, the ones that are of the form.
But 1 second, but they will not be identity, you know?
I'm sorry?
If it's -1, they will not include the identity, no? See? Is it the same or not?
I'm sorry, I apologize. Let me turn my sound a little louder.
No, I say if it's the question of Giulio, if it's -1, it can include the identity.
Of course, yes.
And so
Right.
isn't there
So there will be some matrix. I guess you multiply all of these matrices by the reflection. So it will not be identity, it will be the matrix 1 minus 1 on the
1
diagonal.
minus 1. Yeah, this is simple. No.
Yeah, 1 minus 1 and the other one
See.
minus 1, 1. So just multiply the whole picture by a reflection. I think that's probably true. Well, but they don't form, they don't form a group, I guess. When you multiply to, then the determinant.
No, because yes, because I was thinking to the general group, including also the matrices with -1. That's why.
Yeah.
Yeah.
Okay.
Okay, but anyway,
Yeah,
thanks.
Okay, so how does this stable set sit in this? So let me this is a simple exercise to show that the set of elliptic matrices looks like this. In other words, if you look at the matrices which of the form P times, so take the matrix of the form P R, which is X plus Y, Z, Z, X minus Y, times cosine sine minus sine cosine. And if you ask for fixed theta, that means you fix your location on the torus, right? You fix theta because theta is measuring this angle, right? Because we agree that R, the rotation matrix, is parametrizing the length along the torus. So I want to show that as theta increases, this range of stable matrices becomes smaller. Let me not do this, but basically you can fix theta and see for which x, y, z, which are not independent, of course. X is really, I don't have to list because it's dependent on z, y and z, right? Like we said before, here's this entry X is determined by the other two guys, y and z, by virtue of determinant being one. Anyway, so fixed theta, and you will see that for which y and z the trace of PR is less than 2. It turns out that as theta increases, the range y and z, kind of a circle that y and z describes, shrinks. Shrinks as well, actually, let's see, opens. As you travel starting from identity, it opens. You see, if you start with identity, it's easy to perturb identity to violate stability. If you don't, but if the matrix, it turns out, okay, I am saying too much. Let me just say one thing. Instead of just one little item. So here's elliptic matrices, the set of elliptic matrices obstructs the torus So in other words, if you take a matrix that whose PR, whose rotational part goes around the torus, that matrix must pass through stable set. So this is what I'm claiming. And the proof is trivial. Any matrix PR with R a 90-degree rotation, in other words, 0, 1, minus 1, 0, is elliptic, i.e. it has a trace less than 2, i.e. PR is similar to rotation. So it's some matrix T times this rotation by 90 degrees times T. So it doesn't matter how many times you iterate, what power you take, so it's bounded, right? Because PR to any power is just going to be the same thing, T inverse T times R, a rotation by pi over 2 times n. And that, of course, is bounded. This matrix R is just either identity or minus identity, or, you know, it only takes on 4 values. Okay, so here's a very simple proof. So it's just an elementary linear algebra. I want to show that take any positive definite matrix P and a rotation by 90 degrees, it's a stable matrix. So let's say V1 and V2, these are eigenvalues of P. And they're orthogonal because P is symmetric. And furthermore, lambda1, the corresponding eigenvalues, and lambda2 is a determinant of P, right? And that's 1. So the eigenvalues are reciprocal. So let's see what happens. What does PR? Let's apply PR to eigenvalue V1. Well, R, you see, R is the rotation by 90 degrees, right? So R V1 is V2, so it's PV2. So that's lambda 2 V2. So we discover that one application of of PR to the first eigenvalue gives you the second eigenvalue times, sorry, second eigenvector times the eigenvalue. Let's do this again. Let's apply PR to lambda 2v2. See, I took v1, applied PR to it, and then I apply PR to the result again. So that's lambda 2. Rotation of v2 gives minus v1, right? I factor lambda 2. P applied to v2 is minus v1. And there is P in front. And P applied to V1 is lambda 1 V1. And that's 1. So the upshot is, if we apply the matrix PR to V1 2 times, we get V1 with a minus sign. The same, of course, is going to be true for V2 because my argument is symmetric. I could have chosen V2. So we conclude that PR squared is minus identity. And therefore, all powers of PR are bounded. So PR is an elliptic matrix. So that means that when theta, you change a matrix and its theta changes, the moment theta is equal to pi over 2, the matrix has to be stable. We don't know where exactly is this matrix in the disk, but we do know that it is stable. So any matrix in this disk is stable. Okay, so that's the end of the discussion of the SL2R. And let me just say in a couple of minutes, what does this have to do with a pendulum? I remember I was walking down the street and I stumbled on a piece of broken concrete, and then I realized at that instant that this picture that I just described explains why an inverted pendulum has to be stable. So let's look at the equation of the pendulum, which I write as x dot equals to the matrix, and it's linearized. So x was the angle and the angular velocity of the pendulum, and a is the matrix. It doesn't really matter, 0, 1 minus q, 0, where q is the coefficient of x in the differential equation. The differential equation was this. Let me not write it, it doesn't matter. Okay, so we can write x of t, this is the vector at time t in the phase plane, right? So we have the phase plane x, we have the phase plane x, whose coordinates are the angle of the pendulum and the angular velocity. And we can write x of t is the fundamental solution matrix at time t times initial conditions. So in other words, if I start with the vector x of 0 and wait time t, this vector x of 0 ends up in a new place, x of t, and the matrix F is what sends it to x of t. So, and let me do one more step. So I can decompose F as determinant 1 for all time because the flow is preserving area. So I can write it as a positive definite matrix times a rotation matrix times the initial vector. And this is x of t. This equation links physics with geometry. On the left-hand side, we have physics. We have the angle, we have the vector x, whose horizontal coordinate is just the angle of the pendulum. So for example, if the pendulum, imagine what happens when the pivot of the jigsaw accelerates down. It feels to the pendulum like the gravity points up. And if the pendulum was very short, which is not the case in this experiment, but if you imagine the pendulum being very short, then it will oscillate many times on the downstroke, right? The short pendulum will oscillate down many times while the acceleration is down at the pivot point, right? What does it mean? So that's a physical observation. So as the length of the pendulum, which I choose to be a parameter, becomes small, x of t oscillates many times during the period of one up and down motion of the jigsaw, right? Of course, it happens on the downward acceleration. So what does that mean? So here is this vector goes, when the pendulum oscillates, so not x of t, theta of t, the angle oscillates. But what does it mean in the phase plane? If theta goes left or right many times, that really means that the vector rotated many times. X of t rotates many times during this period, right? So during one period, the vector in the phase plane rotates many times, this vector. Well, what does it say? Here is a vector and these are matrices. P is a positive definite matrix, which notice that a positive definite matrix, what does it do? It simply stretches along one direction and shrinks along another. So any vector stays in its quadrant. When you do this, the vector is confined to a quadrant. So positive definite matrix cannot rotate anything by more than 90 degrees, not even by 90. So all the rotation is due to R. That's the key link. So we, from physical understanding that the pendulum does many oscillations, we know that the matrix, the rotational component of the Floquet matrix, rotates many, many times during one period. So that means, let's look now at this matrix PR. It lives in our torus. It starts as an identity matrix. And as time goes from 0 to a period, this matrix did many, many, many revolutions and ended somewhere. So this is a matrix PR at time t, at the period t, right? And the number of rotations is big. Now what's going to happen when I make, so far I had fixed the length of the pendulum, but now let me make the length of the pendulum shorter. This curve that I just drew, this path of the matrix, will gain more and more rotations around the torus, right? So in other words, this point, this matrix PR, as a function of the length of the pendulum, will itself go, the snake will become longer and longer as the pendulum gets shorter and shorter. So this point will have to execute infinitely many rotations as the length of the pendulum goes down to 0, and therefore there is an infinite sequence of lengths for which this matrix lives in the shaded set of elliptic matrices. So this proves that there exists a sequence of intervals, so I'll just draw a picture, length L, and there is a sequence of intervals of length for which the pendulum is stable. Admittedly, it's not that parameter range which the experiment shows, but at least it shows that topologically, just a topological argument. The only analytical part of this argument is the need to show that the pendulum oscillates many times, but that's a very simple thing by comparison with a constant acceleration. It's trivial to show. Okay, so Yeah. I think I'll stop here. It's probably enough. I wanted to discuss, to describe, but I don't have the time, and some open questions, for example, if you look at the different but related problem of motion of a particle in a rotating saddle. For example, if you have a, just to give a flavor, if you imagine an elongated asteroid, no vibration, but now rapid rotation. So this asteroid is elongated and rotates very fast. And if you look at the particle of dust somewhere that feels the gravitational, oscillating gravitational field of this asteroid, there is a remarkable thing that I don't think anyone understands. It looks like if you average the motion of this dust particle, it is subject to a fictitious magnetic force. Of course, it's not magnetic, but mathematically, it's the force that's perpendicular to the velocity of the particle. So the particle kind of jiggles because the gravitational field jiggles, and but there is kind of an averaged motion like of the particle. If you kind of eliminate these jiggles by change of variables, so there is an average motion, and that average motion is like a fictitious particle, which is a subject to this quasi-magnetic force, so the force perpendicular to the velocity. So, and that's basically done by blind calculation, but I don't understand geometrical reason for it. There's got to be, I think, but I couldn't figure it out. So I'll stop here.
Thank you very much, Mark. I was saying that this lecture are a philosophy of mathematics. They make you think about it. Thank you. Thank you very much. So we would like to thank you for all the 4 lectures. So please open the microphone to thank Mark
you.
with me. Thank you. Thank you.
Well, thank you very much for inviting me.
No, it's a luxury. It's a luxury. And so if people want to ask some questions, please get some questions.
This result about the asteroid, I was interested. You know,
Yeah.
here we are this group of celestial mechanics. So when you mention asteroid,
Yeah.
Is it a paper published?
It's we have an article with it's not formulated in terms of an asteroid, but it's basically any potential a potential. Yeah, we have an article with Graham Cox, which says this, that if you have a rotating, doesn't have to be rotating, but for example, rotating potential for a field, potential force, then it gives rise to this, yeah.
Give us the reference for you.
Yeah, I'll be happy to give you the reference. I'll send you the reference. Mm-hmm.
Yeah.
So I'll send it to Stefanella.
Yes, I understand.
Mm-hmm. I'm just writing it down so I don't forget.
I just want to say to the people of Pisa that we had Angel Jorba given some astrodynamics.
Ah, see?
Yes.
You had or you will have?
No,
sorry.
we had, but the videos,
you had.
And if you want, I can send you the slides. The videos are on the webpage of the school.
Okay, and thanks. Yes, we know him quite well.
Invariant manifold.
Invariant manifold, yes.
Yes, and so I can send you the slides.
Thanks.
But
yes,
the videos are there, and also Deberto give a course also last on stability. So we have all the material.
I see.
There.
Thanks, Stefanella.
No, nothing. Actually, maybe next year some of you would like to speak in our course, because it's a circulating school. So Andrea Venturelli said
Clara and Irene here these are no, I'm joking with them because they are here, the same office as mine.
Andrea Venturelli said that he might give a course on variational method, but
Andrea, yes, I know Andrea.
Yeah, let's see if he confirms. In principle, maybe next year he will give a course on variational
Yes,
method.
I know also Ezekiel Maderna.
Yeah, Maderna, yes, he's visiting. Yeah, okay, so more questions for Mark, since we have
Mark, I would like to comment. I liked the lecture. I lost the last one, the previous one, but the 3 lectures that I watched, I found very interesting, and today, especially the exposition about the Gelfand-Lidske way of finding the stable matrices with that pinched torus. I enjoyed it, and I liked it very much. So thank you for the good lecture that you have given it to us, and that's
Thank you very much. It's really good to see you again. Yeah.
Yeah, very nice geometrical picture. I totally agree with Eldebert.
Yes, I also completely agree. I was very interested about this last part also.
Yeah, I think it should probably be in many books somehow. For some reason, it's.
I never seen it, but if you have a reference, I would be happy. You know, it could be interesting to motivate.
Yeah, I will see. I don't remember. Yeah, I must have it. I'll try to find it.
I think the original paper by Gelfand-Lidske has this picture.
That's right. That's where I learned it from.
Do you have the article? Well, if you can send me the article.
I probably have the reference to that article in one of my.
There is it's a Russian, but I think there is a English version of this article. I guess I can get it, and if I get it, send to you.
Thank you, because I remember once I had to review a Russian paper, and the reference were in Russian, and it took me a while to Google Translate understand something. My Russian is not so good. But eventually I could translate half of it, but if it's in English, it's better.
The Gelfand-Lidske paper is translated into the translations of American Mathematical Society. I don't remember the year, but in the 50s.
But if someone has it, please send it, please.
Okay.
Yeah, I will look for it. When I was in graduate school, we had to take and examine 2 languages, so you could choose between German, French, and Russian. And so I chose French and Russian. And the funny thing is I spoke Russian better than anybody else at Courant, obviously. But I think I was the first Russian student there. But the funny thing is they gave me an article in Russian to translate. I think they just wanted the translation. I don't think they wanted to test if I know Russian, because I don't think anyone doubted that. I think they just wanted the translation.
You know, in Italy, when I started, we had to choose the first year some languages, and we had a teacher teaching Russian. Yes, the first year, theoretical physics. But we had, you know, it was first year, and we had analysis 6 hours, and physics 1 and geometry and so on. And I realized that learning Russian was equally demanding. So I couldn't go beyond 4 or 5 classes, because, you know, already to learn the alphabet was hard at the beginning. So yeah.
But French was very easy. If you speak any of the Latin languages or even English, French was really simple.
Yeah. Well, you know, phonetically, not so much. It took.
No.
Phonetically, yes, maybe it's not so much.
I was very happy about some special classes at the Sorbonne. They do just phonetic classes, so that really helped me. By the way,
I once heard a lecture by a well-known mathematician in French. I was in Paris and I went to hear his lecture, and I never studied French except for the 2 days before my language exam. And I understood almost everything he said because his accent was so bad. He spoke basically,
Poi non vi ho
I
chiesto
would
per
think he
il
spoke
lavoro
Russian, but he
sulla
used
sfera di
French
influenza che
words.
siete trovate con Giovanni.
I'm sorry.
no, I think it was an internal message.
Oh, okay.
Ah, so sorry. Sorry, I'm sorry.
Oh, that's completely okay.
When I took my doctorate degree, usually people from Brazil used to choose German and French. I decided to choose German, Russian and French. Then I took some courses in Russian and could
I didn't know
pass
that.
the exam. And later on, this helped me very much because it's quite a rich literature. And that decision to take the Russian exam in my qualifying was very important for the future.
Yeah, you also translate, no? You do translate Marquez's work? No?
Yeah, I can translate, but not speak.
Yeah. Yeah, no, I wish when I went to Russia, I tried 10 days, but it was not enough. I should study more. Well, next time maybe. So thank you very much.
Thank you very much.
And just to advertise, next course will be Thomas Alarcon from the Theorem of Barcelona. We'll talk about stochastic equation with some application into biology, I think. And that will be at the end of November. And that will be the last course of this semester. But then we will be next semester again, as I say, I hope Andrea Virturelli again about celestial mechanics. So we try to keep going, covering different area. Okay, so thank you very much, Mark. Thank you for a wonderful journey. So bye-bye, everyone.
It was nice to meet you.
Bye-bye, Gilberto. Good to see you.
Bye, Stefanella.
Good to see
Bye-bye.
everyone. Bye-bye,
Thanks,
Giulio.
thanks to everyone.
And
Thanks.
think of Giulio about a course also.
I will think.
Okay.
Thank
Ciao,
you.
pessoal.
Ciao, ciao.
Okay.
Ciao.
Thanks.
Bye-bye. Bye-bye.
Bye.